Welcome back, my friend. In August 2019, the small sailing yacht, Ganesha, entered a vast white sea south of Java. Tonight, we follow its crew across glowing water, later confirmed from space. Settle into a comfortable position, soften your breathing, and let the quiet ocean carry you toward sleep. Subscribe to Deep Sleep Storytelling for more peaceful journeys through history, science, and the mysteries of the sea. Sailing on snow south of Java. 14 years after the faint light of the SS Lima's Milky Sea was recovered from a satellite archive, the White Ocean appeared again. This time, it was not encountered by a merchant vessel or a naval ship. It appeared around a small yacht named Ganesha. The vessel was only 16 meters long, a narrow human presence moving through the immense waters south of Java. In August 2019, Ganesha was sailing from Lombok toward the Cocos Islands, crossing a remote region of the eastern Indian Ocean. The voyage carried the crew away from the bright shores of Indonesia and into open water. By night, the nearest land had disappeared beyond the horizon. There were no coastal lights, no towns, no harbors, only the low sounds of the yacht traveling through darkness. The wind moved through the rigging. Water passed along the hull. Inside the cabins, some members of the crew rested, while others maintained the night watch. At around 10 o'clock, one person awoke and looked outside. The sea was white. At first, the sight may have been difficult to understand. There was no moon, no silver path lay across the water. No low cloud bank appeared to reflect light from a distant coast. The sky remained dark above the vessel, yet below, the ocean stretched away in a pale and continuous glow. The brightness seemed to come from beneath the surface. It did not fall from the sky. It did not rest only on the tops of waves. The water itself appeared illuminated. The glow extended outward from the yacht until it altered the entire horizon. Darkness remained overhead, but the ocean beneath it had lost its familiar blackness. The boundary between sea and sky seemed uncertain, just as it had for sailors crossing Milky Seas in earlier centuries. The crew came outside. They looked over the sides. They watched the pale water move beneath the hull. The yacht seemed to be sailing across snow. The comparison came naturally. The White Sea was not brilliant like daylight. It did not reveal every detail of the deck, but against the moonless darkness, its broad and steady glow transformed the surface into something resembling a vast snowfield. The image was almost impossible. Snow belonged to mountains, winter roads, frozen fields, and cold northern landscapes. Here, the air was warm, the ocean remained liquid, waves rose and settled beneath the vessel, yet the visual impression was the same. A pale plain extended in every direction, and Ganesha moved across it like a small dark shape traveling through a world covered in white. The crew noticed something even stranger. The bow wave appeared dark. Normally, when a vessel passes through bioluminescent plankton, movement creates brightness. The bow cuts through the water. The wake flashes. Small organisms respond to disturbance, producing sparks, streaks, or brief explosions of blue-green light. But in the Milky Sea, the surrounding water was already glowing. The disturbed water near the bow seemed darker than the luminous field beyond it. The yacht's movement did not create the light. It interrupted it. The bow wave opened a shadow through the pale surface. This detail echoed earlier descriptions from sailors who had crossed similar regions. The sea did not flash only where the hull touched it. The glow remained continuous before the vessel arrived and returned behind it after the waves settled. The crew watched the dark wake form across the white ocean. The effect strengthened the feeling that Ganesha was not merely moving through water, it seemed to be cutting a narrow path through light. The vessel continued forward. There was no obvious edge to the phenomenon. No dark band appeared ahead. No ordinary ocean waited at the horizon. The pale sea stretched beyond the limits of vision, giving the crew no way to know how large it was. From a yacht only 16 meters long, the surrounding region felt limitless. The crew could see a few kilometers at most. Beyond that, the glow disappeared into distance. They were inside the event. Its full shape remained hidden from them. Far above, however, modern low-light satellites had already begun observing the same part of the ocean. These newer instruments were more sensitive than the sensors that had recorded the Lima event in 1995. They could detect faint nighttime features with greater detail and distinguish broad oceanic light from many other sources. The crew aboard Ganesha did not immediately know what the satellites had seen. From the deck, they experienced the Milky Sea, as sailors always had, with human eyes, with uncertainty, with a sense of scale that no photograph could fully preserve. Still, they carried modern cameras. They attempted to record the sight. The task was more difficult than it seemed. A camera does not see darkness exactly as a human eye sees it. Human vision adapts. After time spent beneath a moonless sky, the eye becomes sensitive to weak contrast. A faint glow spread across the entire ocean can appear clear because the surrounding world is so dark. A camera must collect enough light to form an image. If the exposure is too short, the water appears black. If it is too long, the movement of the yacht and waves may blur the scene. The dark sky, pale sea, and shadowed vessel create an unusually difficult balance. The brightness that seems unmistakable to a person standing on deck may become only a faint gray field in a photograph. The crew tried anyway. They aimed their cameras across the water. They photographed the glow beside the hull. They attempted to capture the dark bow wave against the luminous surface. Some images preserved fragments of what they saw. They could not reproduce the full experience. They could not convey the whiteness reaching around the entire horizon, or the sensation of moving through a sea that seemed lit from within. But the photographs mattered. For centuries, Milky Seas had survived mainly through words. A captain wrote in a log. A sailor described the water. A report traveled from one port to another. Sometimes a sketch or remembered account remained. Now there was visual evidence from within the phenomenon. The images were imperfect. The glow appeared weaker than it had to the human eye. Yet, they showed a real vessel surrounded by an unusual, pale surface. They preserved the relationship between the yacht, the dark wake, and the luminous water. The encounter drew a line back across time. In 1854, Captain Kingman, aboard the clipper Shooting Star, had described sailing through a sea that resembled a field of snow. His ship belonged to another age. Its hull was wooden. Its course depended upon wind, celestial navigation, charts, and the judgment of experienced sailors. No satellite moved overhead to map the luminous region. No digital camera could preserve even a faint image. The crew could only write what they had seen. 165 years later, Ganesha entered nearly the same visual world. The vessel was smaller. Its hull, instruments, communication systems, and cameras belonged to the modern era. Its route could be recorded precisely. Its photographs could be stored, copied, and studied. Satellites could observe the ocean from space. Yet when the crew searched for words to describe the sea, they returned to the same comparison used by 19th century sailors. Snow technology had changed. The ocean had not. The same microscopic processes had once again transformed darkness into a pale surface. The same contrast between black sky and white water had altered the horizon. The same strange reversal had made disturbed water appear dark against the surrounding glow. And once again, human language struggled to describe something that belonged neither to ordinary sea nor ordinary light. From the deck of Shooting Star, sailors had looked across an ocean resembling a snow-covered plain. From the deck of Ganesha, another crew saw the same impossible landscape. Between them lay 165 years of scientific progress. Bacteria had been identified. Quorum sensing had been studied. A Milky Sea had been sampled. Satellite archives had revealed light from orbit. Yet the first human response remained unchanged. To stand within such a sea was not to think first of enzymes, sensors, or microbial ecology. It was to look outward and see whiteness where darkness should have been. The yacht continued through the luminous region. Behind it, the dark wake slowly closed. Ahead, the pale sea remained unbroken. The crew photographed what they could and watched what the cameras could not fully hold. For a few hours, Ganesha traveled through a landscape that had appeared in ship logs for generations. A modern vessel moved through an ancient light across 165 years. Two crews used the same comparison because ordinary language still had no better image. The sea looked like snow. The largest living light on Earth. From the deck of Ganesha, the Milky Sea seemed endless. The crew could look in every direction and see the same pale surface stretching outward beneath the moonless sky. The yacht moved through it for hours, yet no clear boundary appeared ahead to those aboard. The glowing region was larger than sight, but from space, its true scale began to emerge. Modern satellites carried instruments far more sensitive than those that had recorded the SS Lima event in 1995. Among them was VIRS, the Visible Infrared Imaging Radiometer Suite, designed to observe Earth in both daylight and darkness. Its low-light sensors could detect faint signals that ordinary cameras would miss. City lights, fishing fleets, gas flares, clouds illuminated by moonlight, auroras, airglow, and, under rare conditions, the weak biological light of a Milky Sea. In 2019, VIRS instruments detected an unusual luminous feature south of Java. At first, it was only a faint patch against the darkness of the eastern Indian Ocean. It was not bright like a city. It did not form sharp points like ships. It was broad, diffused, and difficult to separate from the natural background of the night. But it remained. Night after night, the pale region continued to appear. Its shape changed gradually. Its edges shifted. The whole feature drifted with the movement of the ocean. And as scientists examined the observations, they realized that the glowing region was enormous. At its greatest observed extent, it covered roughly 100,000 square kilometers. That is approximately the size of Iceland. The number is difficult to imagine From the deck of a yacht, a person standing beside the rail can see only to the horizon, perhaps a few kilometers away, depending on the height of the observer and the conditions at sea. Even from the mast, the visible world remains small compared with an event of this size. The glowing region could extend for hundreds of kilometers. Its full shape lay far beyond the sight of anyone inside it. Ganesha occupied only a tiny point within the luminous field, a vessel 16 meters long, crossing an area of 100,000 square kilometers, was almost immeasurably small. From orbit, the yacht would have disappeared entirely. Its sails, mast, hull, deck lights, and human passengers would have been too small to register against the vast ocean. Yet to the people aboard, their immediate surroundings had become the whole world. The sea below was white, the bow wave was dark, the horizon had changed, the sky remained black. They did not feel like a point inside a mapped phenomenon. They felt surrounded by an altered ocean. Imagine the view pulling slowly away from the yacht. At first, Ganesha remains clear. The small vessel moves through pale water. Its bow opens a dark path. A faint wake follows behind. The crew stands on deck, watching and attempting to photograph the glow. Then the view rises. The yacht becomes smaller. The pale sea extends farther than before. The horizon that seemed infinite from the deck becomes only a small circle within a much larger luminous region. Rise higher. The yacht becomes a dark speck. Then it disappears. The white water continues. Its surface is no longer a seamless plane, but a broad feature with changing edges, shaped by currents and the movement of the upper ocean. Rise farther still. Java appears to the north. The islands of Indonesia form dark outlines between sea and cloud. South of them, the glowing patch drifts through the eastern Indian Ocean. From this height, it does not resemble a brilliant lamp. It is faint, almost uncertain, a soft mark held within a far greater darkness. This difference between the view from within and the view from above is essential. From space, the Milky Sea is weak. The satellite must gather small amounts of light across a large area. Its sensors must separate the glow from noise, clouds, atmospheric effects, and moonlight. The feature may appear only slightly brighter than the surrounding ocean. From the deck, however, the same faint radiance occupies nearly everything the eye can see. The darkness of the sky makes the pale water appear stronger. The continuity of the glow gives it visual power. The sea does not need to shine brightly in an absolute sense. It only needs to shine everywhere. A small light can be ignored. A dim horizon cannot. The 2019 event persisted from late July into early September. It remained detectable across many nights. It survived through roughly 2 lunar cycles. This persistence was scientifically remarkable. Most marine bioluminescence is temporary. A wave disturbs plankton, and light appears for a moment. A fish passes through water, leaving a brief trail. A breaking surface flashes and then becomes dark again. Milky Seas behave differently. Their light may continue for days or weeks. The organisms producing it remain distributed across an enormous region. The physical conditions supporting them must persist despite waves, currents, predators, changes in weather, and the gradual movement of water. For the glow to remain visible across 2 lunar cycles, it had to survive changes in the night sky as well. During darker phases of the moon, the satellite had a better chance of detecting the biological signal. As moonlight increased, Reflected light from clouds and the ocean could obscure it. The event itself may have remained present even when the sensor could no longer see it clearly. This means the observed duration may still represent only part of its true life. The satellite record showed a phenomenon that was not merely large, but stable enough to become a temporary geographical feature. For several weeks, the night ocean south of Java contained a living luminous province. Its borders moved, its brightness varied, but it persisted. The Ganesha encounter gave this remote satellite signal human context. The yacht's route passed through the detected region. The timing matched the crew's description of a continuous white sea, aligned with what scientists expected from a broad luminous patch. The dark bow wave supported the distinction between Milky Seas and ordinary disturbance-driven bioluminescence. The photographs, though faint and imperfect, preserved visual evidence from inside the event. This connection was rare. A satellite could detect a candidate Milky Sea without any ship entering it. A vessel could report strange glowing water without satellite confirmation. But in 2019, both forms of observation existed. The event was seen from orbit. It was crossed by a yacht. It was described by witnesses. It was photographed. Its location and duration could be compared with satellite data. Each piece strengthened the others. The satellite feature was less likely to be cloud, noise, or human lighting, because a real vessel had experienced luminous water in the same region at the same time. The yacht's account became more significant because the glow around it belonged to a field detected across tens of thousands of square kilometers. The crew had not merely crossed an isolated patch near the hull. They had entered one of the largest known bioluminescent events ever observed. The phrase "largest living light on Earth" can sound as though the event were intensely bright, but its greatness did not lie in brilliance. A lightning flash is brighter. A volcanic eruption may illuminate clouds. A city can shine more strongly from orbit. The Milky Sea was powerful in another way. Its light was repeated, cell after cell, particle after particle, colony after colony, across an area comparable to an entire country. No single bacterium contributed anything a human eye could see. No single colony could transform the horizon, but the same weak chemical light, multiplied across an immense living system, altered the appearance of the ocean itself. The event connected the smallest and largest scales. Inside each luminous cell, molecules reacted with oxygen. Luciferase helped convert chemical energy into cold light around organic particles. Bacteria reached high densities across the upper ocean. Currents carried those particles across 100,000 square kilometers. Their combined glow became visible from space. The crew aboard Ganesha saw only the immediate surface. The satellite saw only the large faint patch. Science joined the two views together. From within, the world seemed white. From above, the event seemed delicate. From either perspective, its source remained microscopic. The largest lights in nature are not always the brightest. Sometimes their power lies in their extent. A faint living glow, repeated across an area too vast for one person to comprehend. What makes an ocean glow for weeks? The 2019 Milky Sea south of Java lasted far longer than a single night. It appeared in satellite observations from late July into early September. Its shape changed, its borders drifted. At times, moonlight and cloud made it difficult to detect. Yet the luminous region remained part of the ocean for weeks. This persistence raises one of the deepest questions surrounding Milky Seas. How can microscopic organisms maintain a visible glow across an area the size of a country for so long? The leading explanation begins with luminous bacteria. They are likely central to the phenomenon. These bacteria can produce cold light through chemical reactions inside their cells. They may live freely in seawater, form relationships with marine animals, or gather around particles of organic material. In a Milky Sea, the particles may be especially important. The upper ocean is filled with fragments too small to notice from a ship. Pieces of algae, dead phytoplankton, mucus released by marine organisms, waste material, tiny remains of cells and tissue. Each particle can become a drifting habitat. Bacteria attach to it, feed upon it, and multiply around it. The particle offers more than food. It also brings cells close together. As the bacterial population becomes denser, chemical signals accumulate in the surrounding water. Through quorum sensing, each cell detects that many similar cells are nearby. When the concentration reaches a threshold, genes controlling light production become more active. The colony begins to glow. One particle carries one small luminous population. Another particle carries another. Across productive waters, the same process may occur millions of times. Yet luminous bacteria alone are not enough to explain the full event. The sea must first provide the material that supports them. This may be why Milky Seas often appear in biologically active regions. The Arabian Sea, the northwestern Indian Ocean, and waters south of Java can all experience strong seasonal changes in productivity. Sunlight reaches the upper water, nutrients become available, phytoplankton multiply, zooplankton feed upon them, fish gather, microbial communities expand. For a time, the ocean becomes crowded with life. Then some of that life dies. Cells break apart. Organic matter spreads through the water. What appears to human eyes as empty sea may contain enormous quantities of microscopic material. This biological abundance may create the foundation for a Milky Sea. The water becomes filled with possible habitats for bacteria, but abundance alone may still not be enough. The material must somehow remain concentrated. The open ocean is always moving. Waves mix the surface. Currents carry water apart. Wind pushes layers in different directions. Turbulence disperses cells and chemical signals. If luminous bacteria are spread too widely, their population density falls. The chemical messages involved in quorum sensing become diluted. The cells may remain alive, but the collective glow weakens or disappears. For a Milky Sea to form, some part of the ocean may need to resist this dispersal. Currents may gather organic particles into a broad region. Slowly circulating water may keep them together. A front between two water masses may act as a temporary boundary. A thin surface layer may trap bacteria, algae, and particles near the top of the sea. Calm conditions may reduce mixing. The luminous community may then remain concentrated enough to maintain its light. This does not mean the water is completely still. The glowing region itself can move. Satellite observations suggest that Milky Seas drift with ocean currents rather than remaining fixed in one geographical position. Their boundaries shift from night to night. Their shape stretches and bends. A Milky Sea is therefore not a permanent place. It is a living water mass. Its geography is temporary. It travels. Suitable temperature may also help the community persist. Bacteria respond strongly to temperature. Warm water can increase biological activity and speed reproduction, although conditions that are too warm or too cold may reduce growth. Different species have different preferences. The temperature must support not only the luminous bacteria, but also the plankton, algae, and other organisms contributing organic material. Oxygen must remain available. Nutrients must continue to circulate. The balance may be delicate. A small change in weather or current could strengthen the event. Another could begin to break it apart. The depth of the luminous layer remains one of the greatest unknowns. From a ship, the light appears to come from the surface. From orbit, the satellite records only what escapes upward through the water and atmosphere. But how thick is the glowing region? It may be a very thin layer, only centimeters deep, or luminous particles may extend through several meters of water. The brightest concentration could lie just below the surface, protected from wind, while still close enough for the light to be visible. Without direct modern sampling, scientists cannot know the full vertical structure. This matters because thickness affects scale. A luminous sheet covering 100,000 square kilometers, but only a few centimeters deep, would contain a different amount of biological material from a layer extending many meters downward. Both could appear similar from space. Only measurements taken inside the event could distinguish them. Scientists also do not know whether the same species dominates every Milky Sea. The 1985 samples provided strong evidence for luminous bacteria associated with organic particles, but one accidental encounter cannot describe every event. Different regions may contain different bacterial communities. One Milky Sea may grow from one type of phytoplankton bloom. Another may begin with a different source of organic material. Some may contain several luminous species acting together. Others may depend heavily on one dominant organism. The white appearance may be shared. The internal ecology may vary. This uncertainty extends to the biological purpose of the glow. Quorum sensing explains how large populations can activate light production together. It does not fully explain why an ocean-scale glow occurs. Perhaps the light attracts fish that consume luminous particles, carrying bacteria into nutrient-rich digestive systems. Perhaps it reflects ordinary behavior that becomes visible only when extraordinary quantities of organic material gather. Perhaps it supports relationships with other marine organisms. Or perhaps the immense glow has no single large-scale purpose at all. The bacteria may respond only to local conditions. The ocean-wide result may be an accidental consequence of millions of separate colonies behaving in the same way. The event's ending remains equally mysterious. What causes a Milky Sea to fade? The bacteria may exhaust their food. Currents may separate the particles. Wind may mix the surface layer downward. Predators may consume the organisms. Temperature may change. Oxygen may decline. The chemical signals may become diluted until the population no longer produces light. The event may not stop suddenly. It may thin gradually. Its edges may become dark first. Its center may break into smaller luminous patches. Eventually, the biological province disappears into the surrounding sea. Satellites have transformed the search. Modern low-light instruments can identify broad luminous patches over remote water. They can follow an event across multiple nights. They can estimate its size and movement They can compare the glow with currents, clouds, moonlight, and biological conditions. But a satellite cannot collect water. It cannot determine which organisms are present. It cannot measure the thickness of the luminous layer or identify the chemicals surrounding the cells. A research vessel must still reach the event, and it must arrive quickly. Milky Seas form far from major ports. They may drift hundreds of kilometers. Clouds may hide them. The first satellite image may not be recognized until the event is already days old. By the time a ship is prepared and directed toward the location, the glow may have faded or moved beyond reach. Future research may overcome this difficulty by combining many forms of observation. Satellite alerts could identify a possible event soon after it appears. Ocean current forecasts could estimate where the glowing water will drift. Research vessels could alter course. Autonomous floats could be released into the region. Drones might map the surface from low altitude. Robotic instruments could measure temperature, salinity, oxygen, and depth without waiting for a large ship. Water samples could be analyzed for DNA, revealing entire microbial communities rather than only the organisms visible beneath a microscope. Chemical measurements could track nutrients, organic material, bacterial signals, and the reactions involved in producing light. With enough coordination, scientists may one day enter a Milky Sea intentionally. They may observe its first stages, follow its development, map its depth, sample its center and edges, watch it fade. The mystery has become smaller, but it has not disappeared. The white ocean now has a probable biological source, yet its beginning and purpose remain hidden. Somewhere, the ocean may be turning white again. Eventually, Ganesha sailed beyond the luminous water. The change did not come all at once. The pale surface slowly weakened around the hull. Dark spaces returned between the waves. The bow wave, once visible as a shadow against the glowing sea, began to merge again with the ordinary blackness of night. Behind the yacht, the white water continued ahead. The ocean became dark. The crew remained on deck for a while, looking back toward the place they had crossed. No clear boundary could be seen. The glow simply faded into distance until the night once again appeared complete. The wind moved softly through the rigging. The sea passed along the hull. The vessel continued toward the Cocos Islands, and somewhere behind it, the great luminous region remained alive. Far above, satellites crossed the darkness. Their instruments looked down upon clouds, coastlines, fishing fleets, storms, and open water. Among those many signals, the Milky Sea appeared only as a faint mark from orbit. It was delicate. From the deck of Ganesha, it had transformed the entire world. Between those two views, currents carried the microscopic community onward. Particles drifted, bacteria gathered, chemical signals accumulated and weakened. Some colonies remained luminous, others faded. The boundaries of the White Sea shifted slowly beneath the night, far from cities, ports, and coastal lights. The ocean continued processes older than every ship that had crossed it. Sunlight had supported microscopic plants. Those plants had grown and died. Organic material had entered the water. Bacteria had gathered upon it. Currents had concentrated living matter across a vast region. Then, under conditions still not fully understood, the sea had begun to shine. Human beings entered the story only briefly. A ship crossed the glow. A crew looked outward. A position was recorded. A photograph was attempted. Then the vessel moved on. The luminous water remained part of the ocean long after the human witnesses had left it. This had always been the pattern. In 1854, the shooting star entered a sea that looked like snow. Captain Kingman and his crew could not identify the source of the light. They could only describe its color, its continuity, and its immense extent. Their words preserved the event. Years later, the CSS Alabama crossed another glowing region in the Arabian Sea. The encounter suggested that this was not a single isolated wonder. Certain waters seemed to experience the phenomenon more than once. The White Sea returned. In 1985, a research vessel entered luminous water east of Socotra. This time, scientists were aboard. They lowered bottles. They carried samples into a quiet laboratory. They placed drops beneath glass. For the first time, part of the glowing sea was physically collected. The mystery moved from the horizon to the microscope. Luminous bacteria became strong candidates for the source. Then, in 1995, the SS Lima entered a milky white sea east of Somalia. Its crew recorded the time, course, speed, and position with modern navigational precision. Years later, that record was matched with a faint luminous patch hidden inside archived satellite data. The same event had been observed from the deck and from space. The old reports were no longer only stories. They had become part of a measurable pattern. Finally, in 2019, Ganesha crossed the vast white ocean south of Java. Its route aligned with a modern satellite-detected event. Its crew described the sea as snow. They photographed what they could. The satellite showed the enormous scale. The yacht supplied the human experience from within. Technology, eyewitness testimony, and visual evidence came together. Each encounter added something the others could not provide. The shooting star gave language. The Alabama gave recurrence. The research vessel gave samples. The Lima gave precise coordinates and orbital confirmation. Ganesha gave modern photographs and a direct connection to sensitive satellite imagery. No single vessel solved the mystery. No single generation understood the whole. Knowledge grew slowly. One generation recorded, another collected, another searched old archives, another watched from space. Each carried a small light into the darkness. The process resembled the luminous bacteria themselves. One cell alone produced almost nothing visible. One ship's report could be doubted. One bottle could not explain the whole sea. One satellite image could remain uncertain. But when observations accumulated, they began to illuminate one another. The record became stronger. The old pages gave meaning to the modern sensors. The sensors confirmed the sailors. The samples connected the glow to living cells. The photographs gave the distant satellite patch a human horizon. Understanding emerged through accumulation. Still, the ocean remained larger than every explanation. Scientists could describe the chemical reaction that produced bacterial light. They could explain quorum sensing. They could identify productive waters, currents, organic particles, and suitable temperatures. They could map the drifting glow from orbit. Yet they could not reliably predict the next Milky Sea. They could not say exactly where the first luminous colony would appear. They could not determine why one bloom became white while another remained dark. They could not fully explain the ecological purpose of the immense glow, and they could not always know when the event would end. The mystery had become clearer. It had not become small. Perhaps that is fitting. The ocean does not reveal itself all at once. It offers fragments, a light seen from a deck, a sample held in glass, a pale signal stored in an archive, a photograph too faint to match the memory, a drifting region detected beneath clouds. Each fragment brings the explanation closer, but beyond it remains a world of moving water, hidden layers, microscopic communities, and temporary conditions that no instrument can observe completely. Now imagine the Indian Ocean at night. There is no storm, no moon, only a warm breeze passing over calm water. The nearest city lies far beyond the horizon. No harbor light reaches this place. No coastline interrupts the darkness. The sea moves slowly beneath a field of stars. Near the surface, particles drift through the water. They are fragments of algae, remains of microscopic plants, soft pieces of organic material, too small for any sailor to see. Bacteria gather around them. The cells feed. They divide. They release chemical signals into the water. At first, the molecules disperse. The population is too small. The darkness remains unchanged. Then more cells arrives. More signals enter the water. The concentration rises. There is no sound, no leader, no central command. Each cell detects the same invisible threshold. Inside one bacterium, the chemistry of light begins. A molecule changes. An enzyme acts. Oxygen enters the reaction. A trace of cold light appears. One cell begins to glow, then another, then hundreds, thousands, millions, billions more. The light spreads from particle to particle, colony to colony. The current carries the luminous water outward. The pale region widens. Fish pass beneath it. Some rise toward the glowing fragments. Others move through deeper darkness below. Clouds drift overhead, unaware of the quiet brightness under them. A satellite may pass above, or the clouds may hide the sea completely. No ship may be near enough to witness the change. No lookout may stand at a rail. No camera may be pointed toward the horizon. The glow does not require an observer. It continues across the empty water, faint, steady, alive. Perhaps it will remain only for one night. Perhaps it will drift for weeks. Perhaps it will cover a region larger than a country and never be seen by human eyes. Somewhere beyond the routes marked on familiar maps, the ocean may already be turning white again. And while the world above the water sleeps, the smallest lights in the sea continue shining together beneath a sky that may never know they are there.